So my previous recording was cut up in the middle of talking about ethanol and polypropylene glycol. So they will, I guess, mixed up. They'll get mixed up with water to make your drug molecule to be more soluble. That's what they would do. And then another type of stabilizer will be polymeric amphiphilic agent. It's hard to say, amphiphilic agent, such as captisol and polyethylene glycol. What they would work is, they will interact with drug molecule to form more soluble complexes. By doing so, they will increase the solubility about 2 to 10-fold. So there's a diagram there. So captisol, so if this is your API molecule, let's say this is a hydrophobic molecule, then this captisol will have a hydrophobic structure that will interact with your drug, but outside of the captisol itself will be hydrophilic. So it's the amphiphilic nature is what that means. One side is hydrophobic, which can interact with your drug molecule, but the other opposite side is hydrophilic, which will interact with the solvent, the water. So it's kind of forming a kind of protective layer. So then your API can be stably delivered into a patient's body. So once it's injected into the patient's body, so captisol could be come off of the API on the site of injection, and the API will go into your target site. So that's what captisol would do. Okay. And then polysolvate 20 or 80, or the another kinds of twin 20, twin 80. Those are surface active agents that can solubilize drug through forming micelles. So what does that mean? It's kind of similar to the previous ones. Let me see if we have that. So again, like a hydrophobic part of like twin 20 or the other one, like a Triton X100, they can bind with API, but opposite they maybe have a charged part, so that can also be amphiphilic, and they can deliver the drug to the target site. So this is the structure of micelle, as you can see. So these wiggly tails are hydrophobic tails. So your drug active ingredient could be located in there in the hydrophobic part, but outside of this molecule is hydrophilic. Okay, so this is what micelle looks like. Okay, so polysolvate 20, twin 20, or Triton, those are serving the similar role, and they'll make your drug more soluble because they have the charged or hydrophilic head outside. Those things will interact with your solvent water. Okay. And then by doing so, they prevent aggregation of your drug molecule. So aggregation is kind of a random binding among hydrophobic parts of the drug. So if your protein is aggregated, they are kind of randomly forming hydrophobic clump. That's what it is. Okay. So if you have big aggregation in your injectable drug, that could cause allergic reaction. Okay. So that's not good. So those stabilizers are needed. And then antimicrobial agents. So you don't have anything growing in your injectable drug, of course, especially multi-dose dose container. So what that means is like injectable container, like a syringe-filled drug. It's not just you inject once and throw it away. If it comes with multiple dosage in that injectable cartridge, you may have to use it several times before you throw it away. Then by using it multiple times, you may get some contamination going into your drug. That's what your concerns. So to prevent that possibility, prevent anything start growing from inside of formulated drug, you may have to add some antimicrobial substance or antifungal agents in your formulation. Okay. Then what are those antimicrobial or antifungal agents that you can add? Examples are here. 0.01% of the total volume of your drug. You can add like phenylmercuric nitrate and thimerosal. Okay, 0.01% is antimicrobial. Or phenol or cresol up to like 0.5%. And chlorobutanol 0.5% is a well-known antimicrobial formulation component. But these, when they are added to your formulation, they should not interact with, with other formulation component. That's important. So they should be carefully tested. Okay. And protein pharmaceuticals like insulin, human growth hormone, interferons, and vaccines, normally they use as a multiple dosage formulation. So it's not just one shot and throw away. And they may, one formulation container may be used multiple times. That's what it means. But some other ones like a tissue plasmid inactivator and the interleukins, it's just a single dosage form. Okay, so if it's a single dosage form, you don't have to have antimicrobial preservative in your formulation, but multi-dosage form definitely should contain microbial component in your formulation. So if it's a single dosage container, it should be used promptly and then thrown away, right? So before it's used, you have to take care of that if it's not exposed to air for a long time, and it should be refrigerated. Makes sense, right? And then buffers, you heard what buffers are so many times. So they are the agents that resist the pH change. By doing so, they can protect your active ingredient. Okay? So by maintaining the pH, you can prevent degradation, aggregation, or precipitation of the active pharmaceutical ingredient, the protein molecules. So buffer system should have a low buffering capacity as feasible as possible, so they do not disturb body's buffering system. Okay, when injected. So your natural body's pH condition is a little, almost neutral, but maybe a little bit acidic, pH 6.7, something like that. So hopefully your formulation pH is not very far off. That's what it means. Okay. And then antioxidants. If your API is very susceptible for oxidation damage, you need to provide some antioxidants in your formulation. So oxidation damage will not happen on your API. Examples are sodium bisulfite and other sulfurous acid frequently used as antioxidant. Sodium salt or EDTA, it's a strong chelator. Okay, so they can enhance the activity of antioxidant by chelating the metal ions. So normally metal ions, a lot of them are transitional metal ions, meaning they can receive and donate electrons frequently. If they can donate electrons frequently, then the outside environment of them will have oxidation. If they take up electrons from their environment, the chelating agents. Okay, if they donate electron, then other molecules will be reduced. So it's a change of electron composition. That's pretty much oxidation reduction, right? So you don't want those. So you want to remove those chelating metal ions. How do you do that? By sucking up those metal ions with EDTA. Okay, that's what it means. So oxidation is initiated by the formation of free radicals like hydroxyl radical and the superoxide and things like that. So then how do you form those? By normally temperature fluctuation. If your temperature goes up too high or if it drops down too fast, then you will see the free radical formation. Okay, or sometimes under the high pH condition or high strong light condition. Again, metal, exposure to metal and peroxides. All of these conditions can be causing oxidative stress. Okay, so to prevent that, you want to maybe maintain a very constant temperature, the pH, and probably avoid the strong light exposure and avoid heavy metal and all those peroxides and things like that. So now oxidant could be the source of oxidation again. So if your API is susceptible, really susceptible for oxidation, then you may have to remove oxygen from your primary container. So you have to displace oxygen in your container and maybe fill that container with inert gas like nitrogen. Okay, so that's how you can prevent oxidation. So the isolator technology, and then the filling machine, so that filling machine isolator is kind of sealed environment, so you can fill nitrogen during your vial filling. That's possible. And then tonicity agent, like I said, the salt concentration should be maintained. Similar to the physiological condition of the living cells is what you need. Okay, so isotonic is possible. Okay, maybe about 20 to 50 millimolar salt concentration is what you need. Okay, physiological fluid. So injections into subcutaneous tissue and muscular tissue should be isotonic, because you don't want to cause any cell damage because of too much salt going in or too little salt going in. If that happens, you'll feel a lot of pain and irritation around the injection area. So if it's needed, you can add electrolytes like sodium chloride, table salt, glycerin, or mono and disaccharides can be added as a tonicity agent in your formulation. Makes sense? And then I talked about cryoprotectant and lyoprotectant. Cryo is against freezing. Lyo is against drying. So if you have to freeze dry your drug, you may have to add these. Okay? So normally sugars, sucrose, trehalose, or polymers. Polymers are polymer of sugars. That's what polymers are. And liquid polyethylene glycol or dextran, they are used as cryo and lyoprotectants. So excipients that are excluded from the surface of the protein are the best cryoprotectant. Okay, so what that means is excipients that are binding with the API. Okay. Excipients that remains amorphous during and after freeze drying, so best as lyoprotectants. Amorphous, we'll talk about that when we talk about the freeze drying. Okay, it's a condition of freeze drying state is what amorphous is. There is eutectic, amorphous. We'll talk about eutectic is better. Okay. And competitive binder, again, if your API is strongly binding with the containers and things, if your API sticks to the container, then you will lose it because it doesn't come off and doesn't go into a patient's body when you give them injection, right? So you want to prevent that binding of the API on the primary container. How do you do that? By adding competitive binders. Okay, so these are the agents that are used to compete with active ingredient. So instead they are binding to the container, like I said, or the manufacturing equipment surface, like maybe tubing in the sealing machine, or maybe seals that are placed and things like that. So examples are polysorbate 20 or polysorbate 80. They are commonly used as competitors. So by themselves, there is no pharmaceutical, effect when they are injected. So a little bit of them is normally used as a coating material, okay, in the formulation. Other additives, bulking agents. Your API has a very small structure, and then you may add these bulking agents. Okay, especially for freeze drying. If you don't have bulking agent, your freeze dried drug may collapse, and that's not pharmaceutically elegant structure. So to provide visual good sustained structure after freeze drying is done, you may need to add a bulking agent. Okay. Or suspending agent in other name. Okay, wetting agent for emulsion, viscosity inducing agents for ophthalmic product. Ophthalmic product is what, the eye care product. Okay, so those are other additives. So normally made up with the polymers. Okay, so mannitol is a good example. So we'll talk about them later on.